Steinhauer here. Welcome back. I have a question for you that involves Newton's laws and applying them. So you have a person here who is, we're seeing from looking down on this person from above, and this person is swinging a rock that's tied to a rope over her head. And the question is, so this rope's going to snap at some point, and it's going to snap when the rock is right there. And the question is, what is the path that the rock will take after the rope snaps? So we'll go ahead and show this animation. There it goes. The rope has snapped there. The question is, what will the path of the rock be? Will it travel in A? Will it travel in B? Will it travel in C, D, or E, continue around in the same trajectory? So pause the video, make a guess, and we'll come back and talk about it. Okay, so we need to know some things about this rock. In which direction is its velocity pointing at this particular place? Its velocity is the instantaneous direction that it is moving when the rope snaps, and that is most decidedly in this direction. This rock was traveling in this direction. The acceleration at this point was not in this direction. The acceleration was provided by the rope, which is provided by the force of tension in this rope, which was decidedly in this direction. But the velocity at this particular point was due in this direction. And according to Newton's first law of motion, objects with no forces acting on them, objects in motion tend to stay in motion. Objects don't change in velocity unless there is a force acting on them. And so it should be the case that the velocity of this rock, once you stop acting on it with a force, will continue in the same direction. Let's see if we got this one right. There it is. It will continue traveling in a straight line at its present velocity in this particular direction. So there you go. Newton's first law applied to a rock in this particular case. Okay, moving on. Newton's other big discoveries was, of course, the universal law of gravitation. So here is a formula here is the formula for gravity. The basic idea of gravity is this: every object in the universe that has mass feels an attractive force from every other object in the universe that has mass. And this is an equation that describes that how strong that force is. Essentially, that force of attraction is directly proportional to the product of their masses, mass 1 times mass 2, and it's inversely proportional to the square of the distance between their centers. So the more massive the objects are, the greater the force of gravity. The further they are away from each other, the smaller the force of gravity that is. And you can codify that by this particular equation, Fg equals G m1 m2 over d squared, which we have written in greater detail on the next slide. The thing I want to point out here is d is the distance between the center of these two objects' centers. So the center of m1 to the center of m2 is the distance, is the quantity we would say is the distance between these two objects. Okay, let's take a closer look at this equation. F sub g, the sub g just refers to the fact that this is the gravitational force, is equal to, on the top of the equation, you have these two masses, m1 and m2. It's going to be important as we're using this equation and all equations to understand the units of every quantity involved in this particular equation. So m1 and m2 are masses. The units that we typically use for mass is kilograms, especially in astrophysical contexts. Now, you might be more familiar with using the unit pounds. When you step on your scale, bathroom scale, it probably reads back units in pounds. It turns out that the pound is actually not even a unit of mass. Even though you can probably switch your scale to go from kilograms to pounds, kilograms is not a proper unit for what that scale is measuring. Again, that scale can only measure weight, the amount of force that you're exerting on that scale when you step on it. And so pounds is actually a true unit of force in the English system. Kilograms, it has to make the assumption that you're standing on the scale at sea level on the earth to infer how much mass you have to be causing that much force on the particular scale. But pounds is not a unit of mass, and kilograms is a unit of mass. They're fundamentally different things. Interestingly, the English unit for mass, there is one, is the slug. So no wonder we don't use it for very much. Okay, d, of course, is that d squared is in the denominator. And of course, this is the distance between the two objects. This is a unit of length. So we could use meters or kilometers or inches or light years or whatever we wanted. Now, there is one more thing in this equation, the proportionality constant, right? We have the product of the masses, we have divided by distance squared, and this big G is a proportionality constant. It's a constant. It's just a number. It's a weird number. It's a very small number, in fact, and it's got weird units. And this is it. 6.67 times 10 to the negative 11, and it's got units of meters cubed per kilograms times seconds squared. This is an extraordinarily small number. You get a 0, a decimal point, 10 zeros, and then 667 to get this number. Gravity may seem like a large force, but in fact, it is the weakest of all the forces that we know. And the reason for that is because of this very small constant here. So Fg, of course, is the force of gravity, and it's useful now to know what the units are on force. Okay, so we can do a dimensional analysis. We can do a unit analysis now and figure out, based on the units of G and the units of M's and the units of D, what the units on F have to be. So let's do it. So I'm going to do this sort of square bracket to denote the units of things. The units on F of G must be equal to the units of G times the units of M times the units of M times the unit of D, quantity squared, because that's our formula up there. So the unit on G, I know, is meters cubed on top per kilogram times second squared on the bottom. I've got two masses on top, that's kilograms times kilograms. And I've got a D squared on the bottom. Let's use meters. I've got a meter squared on the bottom. So I can cancel some things out. If I have things on the numerator and denominator, they can cancel out. One of these kilograms, I'll use red. One of these kilograms will cancel one of those kilograms. I've got still 1 kilogram on top. I've got a meter cubed and on the numerator and a meter squared in the denominator. So I can take 2 of these meter squareds and cancel this meter squared and cancel 2 of the meters over here. One of them is left though. M cubed divided by M squared is just M. So, and there are no other seconds. So we've got our form, we've got our unit now. We've got meters on top and kilograms on top and seconds squared on the bottom. Kilogram meter per second squared is the unit of force, which makes sense, right? We also know that force is mass times acceleration. Mass has units of kilograms. Acceleration has units of meters per second squared. So it's not shocking that any force, in fact, any force you do calculate has to have units of length times mass divided by second squared. Now, this is a lot to say. Meters, who wants to say kilogram meter per second squared all the time? Nobody. So to honor the person who came up with this whole concept of force, really, we define this unit and give it another name. This unit is defined to be the Newton. So 1 Newton is the equivalent of three dashes is a defined to be, as opposed to just equal to 1 kilogram times meter per second squared. That's the definition of a Newton. Okay, let's do some questions for you. We're all sitting or standing or resting on the earth right now. if you were to calculate the force of gravity between yourself and the Earth, what would you use for d, the distance? Would you use 0? Would you use the radius of the Earth? Would you use the diameter of the Earth? Or would you use 1 AU? What do you think? Okay. It is, so let's draw the picture actually. I'm gonna draw this greatly exaggerated. Here is the Earth, and here is me standing on top of the Earth. Obviously, I'm much smaller than that in real life. So let's think about these things, right? 1 AU is just silly. That's the distance between the Earth and the Sun. That has nothing to do with the force of gravity between the Earth and me. It's tempting to say 0, right? It's tempting to say 0 because I am physically touching the Earth. I am standing on the Earth. I am sitting in a chair that is on the Earth. And so it's tempting to say that the distance between myself and the Earth is 0. However, that's going to be a problem because if you plug 0 into this equation, no matter what M1 and M2 are, your calculator is going to say, cannot compute, does not work. In fact, as d goes to 0, this force of gravity goes to infinity. Now, that is not the case. I'm not infinitely attracted to the Earth. So d has to be something else. And if you remember, d is the distance between the center of one object and the center of the other object. It's that distance. And that distance is the radius of the Earth. So that's just something to keep in mind when you're calculating these things. It can be tempting. You're gonna be tempted to write 0 for that. But in fact, if you go center to center, that's really the radius of the Earth. Okay, here's another one for you. And this is the kind of question that I like to ask because it doesn't even involve, it shouldn't even really have to use a calculator for this one. This is a question that tests whether you understand how these kinds of equations work. So here's the question. If you double the distance between two objects, what happens to the force of gravity between them? Does it go up by a factor of 2 or 4, or does it go down by a factor of 2 or 4? I'll give you some time to think about it and then come back and we'll discuss it. Okay, so I am increasing the distance. I'm doubling the distance. I am increasing d by a factor of 2. G and M1 and M2 are not changing at all. The only thing that I'm changing is d. And so that gives me, all I have to do is think about how F is related to d. And since d is in the denominator, if I make d bigger, FG has to be smaller because 1/4 is less than 1/2. The bigger the denominator gets, the smaller the total quantity gets over here. So it has to be down. I can immediately eliminate A and B. If the distance between two objects goes up, the force between them goes down. How much? Well, this d is squared, and that's important. That means if I increase d by a factor of 2, I have decreased this whole value by a quantity of 2 squared. And since 2 squared is 4, my answer must be D. It goes down by a factor of 4. If I triple the distance between them, the force of gravity will go down by a factor of 3 squared, or 9. This square in the denominator is a powerful thing. It means that moving things further away has way more influence than changing one of the masses, for instance. Okay. One last concept in this before we move on to another topic, and that is this particular question of why astronauts in space are weightless. And this is an important thing to think about. It's tempting to say, and normally when I ask this in class, and there's a room full of 100 students, and I say, why are astronauts weightless in space? Somebody raises their hand and says, because there is no gravity in space. That is the common answer given, and it's completely wrong. And we can see why it has to be wrong. It has to be wrong because if there were no gravity in space, so let's think about astronauts. To understand why astronauts are weightless in space, we need to bring in another little animation video. So here we see This is actually a drawing from Newton's actual book. We see a very tall mountain, a theoretical mountain that's way bigger from Earth scale than any mountain on Earth. But it doesn't matter. It's a thought experiment. And the question is, what if we were to aim a cannon in this direction and fire a cannonball out of this cannon at a certain velocity? And we're going to talk about a tremendously large velocity, 2,000 meters per second. That's 2 kilometers every second. That is way faster than anything that you would experience in your normal everyday life on Earth. And if we do that, you'll see that the cannonball actually travels quite a ways before it reaches the ground. As we increase this velocity, though, let's say we can fire it at 3,000 kilometers per second, it travels further. And interestingly, if you fire it fast enough, let's go to 4,000 kilometers per second. 4 kilometers per second, 4,000 meters per second. The faster you fire this cannonball, the further it makes it. And in fact, the Earth's surface will start bending away from this cannonball. And so as we go towards 5 kilometers per second, it's going to make it a huge way. 6 kilometers per second, 7 kilometers per second. Going to make it all the way around. Whoa, duck, it's coming back. Whoa, look at that. That's interesting. If you fire it at 7,000 kilometers per second, yes, it was continually in free fall, but it never actually hit the Earth because the Earth curved away from it faster than the actual object fell. If we go to like 7,250 kilometers per second, the cannonball enters basically a perfectly circular orbit and comes back and hits you on the back of the head. It never actually lands. And this is what to be in orbit means. Let's go back and think about this one, right? If you put let's say it's a hollow cannonball and you put a mouse inside that cannonball and you fired it off at 2,000 meters per second, what is the weight of the mouse as the cannonball falls? Let's say just you drop it off of a high cliff. You don't even need to fire it at any speed at all. That mouse is weightless. Why? It's the same reason why a person is weightless in an elevator whose cord has been cut. Both the cannonball and the mouse are falling at exactly the same rate. Both the elevator and the person are falling at exactly the same rate. And so in this scenario, the mouse is weightless inside the cannonball. It's not that gravity isn't acting on them. Of course it is. It's just pulling the cannonball down at exactly the same rate as it's pulling the mouse down. Now, if we increase this velocity to something large, the same exact thing applies. There's a mouse inside this cannonball. They're both falling towards the Earth at exactly the same rate. And so the mouse inside there feels weightless. It's not that gravity isn't acting on them. It's that the cannonball and the mouse are both in free fall around the Earth. They just never hit the bottom because they're moving fast enough that they stay in orbit. That's what being in orbit means. In fact, and that's why getting to space is hard. In order to get to space, actually getting to space isn't hard. Staying in space is hard. To stay in space, you have to get yourself and whatever contraption you're riding in to get to at least 7,250 meters per second, which is really fast. Once you do that, assuming you're above the atmosphere and there's no resistance anymore, you will stay in orbit. You will be orbiting the Earth without exerting any more forces on yourself. Now, interestingly, what if we increase this to, 8,500 meters per second? Let's see what happens here. What do you think is going to happen if I fire it even faster? Let's do it and find out. Whoa. It's not a circular orbit anymore. What is the shape of this? It's going to come back in a minute. Just wait for it. What is the shape of this orbit? You can't see the whole thing, but what do you think the shape of this orbit is? It's an ellipse. what do you think is at the center of the Earth? I bet it's one of the two focus points of this ellipse. And if you watch it again, where is it traveling fastest in its orbit? It's traveling fastest when it's closest, when it at apogee, and it's traveling slowest when it's, perigee, and it's traveling slowest at apogee when it's at its furthest point away. You can see two of Kepler's three laws encapsulated in this cannonball problem just by changing the velocities of various things. So that's why astronauts are weightless in space. It isn't because there isn't a gravity in there. It's because the spaceship and the astronaut are both in free fall, and it's just like cutting the cord on the elevator. They're both falling to the Earth at exactly the same rate. They just are moving fast enough that they never actually hit the Earth. Interestingly, if we get this high enough, the ball never comes back. There is a velocity at which, if you fire it fast enough, that ball will never come back. And that's the last topic in this particular segment of the class. Escape velocity. Here's escape velocity. If an object gains enough orbital energy, it gets fired, or in other words, gets fired from a cannonball fast enough, it will change from a bound orbit to an unbound orbit, a bound orbit to an unbound orbit. A bound orbit are the ones we've been talking about, the circular and elliptical orbits. Unbound orbits do not come back. They are gone. We'll talk about escape velocity is going to become important later in the semester when we talk about black holes. But for now, just know that the escape velocity from the Earth is about 11 kilometers per second, which is not that much bigger than the 7,500 or so kilometers per second it takes to enter circular orbit around the Earth. But if you get things moving fast enough, in other words, if you want to go to Mars or go to the moon, you have to be going about 11 kilometers per second to escape the Earth's gravitational field altogether. Okay, there's one more piece of this. We'll talk about a formula for this, calculating the escape velocity when we get to black holes. There's one more thing I want to talk about in this section, and that is Newton's version of Kepler's third law. So remember, Kepler's third law was p squared equals a cubed, p being in the orbital period in years, a being the semi-major axis in astronomical units. Newton realized that Kepler's third law was a special case of a much more general law that applies to any object orbiting any other object. And so this is going to be important in lab when we do our Kepler's law lab. But this is the more general version of Kepler's third law. It's still p squared equal to a cubed. There's still a p squared and an a cubed here, but Kepler figured out what the proportionality constant was and how it would change for, let's say, an object orbiting the Earth or a moon of Saturn orbiting Saturn. And this is the formula. P squared equals 4 pi squared divided by this g again. This is the same g from the force of gravity equation. It's Newton's gravitational constant times the sum of the two masses. So in the case of the moon orbiting the Earth, it's the sum of the mass of the Earth and the moon. In the case of a moon orbiting Saturn, it's the sum of the mass of the moon and Saturn. Now, since g comes in units of meters and seconds and kilograms, and these masses come in terms of kilograms, p and a have to take their units from these. So this is no longer an equation that you plug in years and get out astronomical units. This is now an equation that takes its units from whatever units you plug in for g and m1 and m2, which are typically going to be seconds and meters in the case of p and a. Okay, we'll stop there, and next week we will move on to thinking about light.